Hi, welcome to the Calculus 1 lecture series. And we are in the unit number 4. We are talking about the integrals. And we are in the lecture number 26. And this is our second video for this unit. We're going to talk about the definite integrals. Our first video, we are talking about how to approximate the area under the curve, right? And then we defined what is the definition, the area under the curve. And so today we're going to, continue that concept, and we're going to define what is the definite integrals and how is that to do with the areas here. Okay, so now let's go ahead and go to our lecture notes. So let's try to write down some definitions here. Okay, so first let's take a look. What is the definite integrals here? And first, the definite integrals, we are for functions, f of x, right? So we are writing like this. This is our symbol. We say is a to b is in a fixed interval, and this is, we call this f of x dx here. Okay, and this is the definition of the definite integral. That's what we write it, but what's that means here? So the first things we need to be very careful here is this dx, right? So this dx basically is just telling you, while I'm doing this, my variables here is x here. So sometimes, for examples, right? So you could have like f of x, right? So you could have let's say the x squared plus t squared plus 2xt. So when you try to do the definite integral, you say ab f of x dx. That means what variable I'm care about, because it's x's, right? So this is x, this is x, and all the other variables in this function we treat as what? As a constant. Okay, and so that's the first things here. We need to be very careful about this dx. The purpose for this dx just telling you, which variable I'm dealing here. All right, then AB, this is the fixed interval. Okay, so what is, okay, so this is, we know how to write the definite integrals here. All right, so now in here, let's write it. So we say that the f, okay, let f be a continuous non-negative, okay, function on the interval AB. Okay, so that's why here you have a ABs here. So if we partition the AB into n subinterval, all right, so now we know that delta x is equal to b minus a to the n. Okay, and then also we choose xi star. Remember, that's what we call this random sampling points, right, from the previous video. So we set the xn star to be any point, okay, from the IC interval. And then we defined, so we can define this definite integral. We say is a and b. Then we say this is f of x dx. And these ones here, we can define this limit and approach to infinities, right? So summation I from 1 to n, and this is f of xi star and delta xi is here. So if limit exists, okay, then we say the f of x is, integrable on AB here. Okay, and so in here, let's highlight a few things here. So be careful. So in here, the f has to be a continuous and non-negative functions here on the interval AB here. And so in here, we said that this point can be any points, right? So from the previous video, we are trying to practice, we said we can use right endpoint, left endpoint, or middle point. But in fact, you can choose any point. So we say then the AB, the f of x dx. So this is a definite integral will be the limit. That means you partition this interval into infinity numbers of the subintervals here. You remember from our first, from our first video, we say, what is here? Right, so what is this things here? What is this we highlight? This is what here? This is the area, right? So this is the area under like the curves here, right? So under the f of x. So we say if this limit exists, then we say f of x is what is integrable. That means you can integrate that over the AB. So basically from here, we are trying to find the area under this function f of x. And also from the previous one, we said the Riemann sum. What is the Riemann sums here? So we said the Riemann sum is this, right? So it's I is from 1 to infinity, 1 to n, f of xi star times delta xi. So this is what we call the Riemann sum. So if you let n approach to the infinity, then the Riemann sum will be find the integration for here. So basically in here, this is the same thing like I say. Now we know, oh, when we think about take the integration, we are taking about the what? The area under the curve. And then like we said, also in here, we say this is the non-negatives, right? So we say be very careful. And I think in the video number 4, we're going to talk about is take a look. How about if I have my function is like it's not a non-negative? Then how do I define definite integrals here? Okay, so right now, that's why from this definition, we know the definite integrals is try to find the area under that curves here. All right, so let's take a look at some like the simple problems here. So let's take a look at in here. All right, so the first problems here, let's say if the delta x is equal to 3 minus 1 over this interval, this is from the 1 to 3, and the xi is any number inside this subinterval, then this is what the area is a summation I from 1 to n. So this is xi to the 4th and the delta x's, right? So let's say what is the function, right? So what is the limit for this, right? So we know the limit here, this is the area. So this limit is equal to what? This limit is equal to, like we take the integrations, the a to b. Then what is your f of function? So here, take a look here, right? So this is what we did. We said this is f of xi. So this is f of xi here. So what is your f of function? Your f of function is what? Is the x to the what? X to the 4th. right? So for every subinterval, then is extra the force, and then don't forget you do a what dx here, right? Of course, right now we have not talked about how to evaluate that yet, but we know we are finding the area of, this is the area definition, so I can rewrite it as a definite integrals here. Okay, so now let's take a look at these ones here. Let's say approximate the 1 to 4 x cubed using the middle point rule with n equal to 3, all right? So if n equal to 3, right? So then I have what? My delta x is equal to the 4 minus 1 divided by 3, right? So what is my delta x here? Delta x is 1. Then we can use what we learned from the first video, because in here they say approximate it, right? So that means I'm just trying to find the sum of those rectangles here. So okay, so these ones here I have 3 subintervals here. Okay, so this is my subinterval. Okay, so let's see. The first one, you are vary from 1 to 4, right? So it's 1 to 2, correct? And then it says I'm using what point? I'm using the midpoints, right? Okay, so now I need to find the xi. So this is xi star. And then I need to have f of xi star. Then I have just like we did from the first video, this is fxi star times delta x. Okay, now let's go ahead. So this is 1 and 2. So what is my midpoint in the 1 and 2? This will be 1 point what? 1.5. So what is my function? So will be 1.5 to the what? Third, right? So this is 3.375. And then my delta x is 1. So function times, so what is this area? 3.375 times 1 will just be by itself. Okay, so my second interval is 2 to 3. So what is the midpoint? My midpoint is 2.5, right? So then the f of x is x cubed, so it's 2.5 to the third power, so it will be 15.625. So the area will be 15.625 times 1. So my third intervals will be 3 to 4. So what is the midpoint? It's 3.5. Then 3.5 to the cube will be what? It's 42.875. Then this is 42.875 times 1. Okay, now I add them together. So you add this column, this will give you 61.875 here. So I know this is like a notation we said, this is the M3s, right? So that's why I can say this is 1 to 4, the x cubed dx can be approximate by 61.875. Of course, this is not the exact area under that because I only took like 3 subintervals here. Okay, so let's do one more. So this one is very similar like we did before. So let's say use the partition to take a look at the 4 equal sides, and I'm looking for the right end point to the sample point, all right? So now let's take a look. How do we do that? So I'm starting from -2 to 4. Okay, so 4 equal sample size. My delta x is going to be what? My delta x is going to be 4 minus -4 and over what? Over 4, right? So my delta x is 1.5 here. Okay, so now let's just like we did previously. So the first things here, then my subinterval, my xi, my f of xi. So all right, so now let's take a look. So this is I. So how many interval? 1, 2, 3, 4. Right, I have a 4 interval. So let's take a look at the first subinterval. Then I have xi star. I have f of xi star. Then I have f of xi star times delta x. Okay, so the first one here is, so we start at -2, right? Then the length is 1.5. So, you add 1.5. So it's stop at the point, -0.5 here. Right? So now I'm using the right-hand rule. So which number I'm choosing? So I'm using the right-hand rules, right? So I'm choosing this number. Okay, so this will be -0.05. Then you substitute to your function is 3x squared. So this is 3x squared, right? Then you substitute 0.05 to here. Then you will get a 0.75. Okay, now what is the area? Will be the 0.75 times the delta x, so it's 1.5. So this one give you 1.125. Okay, now let's take a look at the second interval is from -0.5. Then you go to add 1.5. So we stop at 1. Then you use the right hand point. So this is 1. Okay, so 1, so this is substitute 3, right? So this will be 3 times 1.5, so it's 4.5. Okay, the interval number 3 will be 1, and this is added to 1.5, will be 2.5, right? So you use the right side, right end, so this is 2.5. So 3 times 2.5 square, so this is 18.75. Then in here you will have 18.75 times 1.5. So you will get a 28.125. Okay, the last subinterval will be 2.5 to where? To 4. So my right end point is 4, right? Okay, so 4, you substitute a function 3 times 4 to the square. So it will be what? It's 48. Then this is 48 times 1.5. So this will give you what? 72 here. Now you add all them together. So what do you add this one together? This one will give you 105.75 here. This is go to the right, right? So I say this is R4 Riemann sum, right? So it's 105.75. So that's why I know that here this is -2, 4, 3x squared dx, very close to what? 105.75, right? So this is how do you approximate, right? So in here, so this is how do you approximate, your integrations here, right? So I'm just trying to approximate the areas, right? Under the curves here. Of course, you can do like what we did on the first video. You can partition your interval to the infinity numbers, and then you can find the exact value of this integration. Okay, so now we know, okay, we know what is the definite integrals means, right? So that means, when you when you try to take the integration, it's really you try to find the areas here, right? So now let's take a look some area principles here. Okay, so let's see here, right? So the first thing see here. Okay, so here, let's see here. All right, so let's assume I have a function here, right? So I have a function like go like a ding dong, all right? So then I am going to find this is my A, this is my B here, okay? So we already know the definite integrals definitions. This will be AB, f of x dx, right? So it will be this area in between here. Okay, so the first principles here. So the number one here, okay, let's be careful here. So now this is ABs, right? So if I choose some points in between here, right? So I say this is the C's here. So then you see this area, right? So you can separate become areas, this one and what? And this areas, right? All right. So I know the first things here. I know when the A to B f of x dx, according to our definition from A to B, so it will be the whole this colored area under the curve, right? So if this is my f of x, so if I have anything in between, I can separate that. So I can say this is A, you know, you to the C's, right? So this is f of x dx. So this one will give you the blue area. Then is plus what here? So C to where? C to B here, f of x dx. Correct? So this is our first principles, right? So you can find anything. So it's kind of obvious because the AC, if I kind of color like, you know, the color coding for you, C to B is this pink one, right? And A to C is this blue one. So reference back to the same things here. Okay. So now the next things here, this is also is a very good principle. Okay, so now in here, so this is I'm doing from A to B, f of x dx. How about if I changed, right? So now I change to the B to A, f of x dx. Then what happens here? I'm going to have negative signs here. All right, so this is very, very important, right? So I'm going to have negative sign when I switch the bond. Then you will say they're both in here. Why make any differences? The differences here is this delta x, right? So delta x, you use the upper bound minus lower bound. So it's b minus a to the n. And in here, now this delta x, right? So this delta x is equal to what? Upper bound minus lower bound. So it's a minus b times n. So this will be, so look here, these two, this will just be different than a what? Than a negative number. And then this is a summation f function times delta a, right? So that's why this is where the negative sign come in. So this is the number 2. It's very important about the area principles, right? Because if we switch it, the things that make the differences is this delta x, right? So this delta x, because when you finally find the area, you need to use the, because you say it's f of xi star times delta x, right? So one of them, they are different by a what? By a negative number, negative signs, right? So that's why you need to have negatives here. Okay, so now the number 3 is here. Okay, so if I want to do AB, all right, so here is C dx. Now, what is this one here? Okay, so let's see what is this one here. All right. Okay, so this one in here you said C, right? It's a constant. It has nothing to do with the x. Remember the dx tell you which one. So that means your function is like something like that. So it's a C, it's a constant, it's here. Then here is your A, here is your B, right? And now we see here, we say, oh, okay, then what is my areas here? So A and the B to the C. So what is my area? My area will be here. It's a rectangle, correct? So then what is the rectangle, the length here? The length here, this is the length, right? So this is the length. What is here? This is b minus a. And this is the width. What is width here is c. So that's why in here we can say this one is just equal to the c, the b minus a. right? So for any constant, so it's just try to find the rectangles here. Okay, so number 4 here. Okay, so they tell you if you have AB, all right? So if you have a AB, and then you have f of x plus or minus g of x dx. That means if you are plus minus function, then you can separate that out like f of x dx plus ab, then this is gx dx, right? So you can do plus minus, does not matter. Okay, now the other ones here, this is number 5. So we say if a and b, if you have a constants times f of x dx, that means you just, like if c is 2, that means you just double whatever the area. C is 3, you just triple the area, right? So then the c, you can take it out. So this is the ab f of x dx here. Okay, and then the last ones here, let's see here, and this is number 6 here. You don't really you don't really need to remember, just make, I think it's a concept wide, it's pretty easy to understand, right? It's just find the area. Okay, so now let's take a look. If I have a to a, f of x dx, what is this value going to be? This value is going to be 0. Why is 0? Because in here you take a look, hey, your upper bound is equal to the lower bound. So what's that mean? So that means in here, right, you can have a function. If this is my f of x function, then I'm going to have a, so this is a, I'm going to, from a to a, right? So I'm kind of want to find the area. There's no areas, right? Because it's just a line, there's no area. So that's why this is equal to 0. So this, these 6 properties here give you some very, very basic understanding, right? Fundamental things. So it's kind of the key things to remember, and it's pretty easy also. Okay, so now let's take a look at some example. Those examples are pretty easy example. Let's say I write a definite integral for the shaded area. Okay, so this shaded area, right? So this is the area under what? Under these curves, right? So I know this is also, this function is non-negative. So I know the shaded areas here, I can write it like what? So that means take the integration. What is my boundary? So it's from -1 to where? To 3. Now what is my f of x? My f of x is here, right? My f of x is here. So this will be x cubed over 3 minus x squared plus 2. The whole thing, what? Dx, right? So remember, the dx is just telling you, you are doing the integration from the x here. Okay, so now all this example, I think is pretty good and it's a simple example. Okay, so now let's say sketch a graph that's corresponding to the number. Okay, so look here, let's say the number corresponding to this number. That means what is this number represent? This number represented the areas, right? Okay, so now let's take a look. So, okay, how do we do that? So this is a pi over 2 pi. So this is a negative pi over 2 and negative pi. Okay, so I know cosine here. This is 1. Cosine is something go like this, right? Okay, so here go like this. All right, okay, and then now for this province here, right? So this is my cosine, I already draw that. So my lower bounds here is negative pi over 4. So this is pi over 2. So this is negative pi over 4. So here, and then to the pi over 2. So it's 2 here. So what is this number represent? This number represent the area between those two. Do you get that? All right, so that is what is this graph represent here. All right, so that's what is this number, is this areas here. Okay, now let's take a look. The number 6. Number 6, what is the value 3 to x squared plus 1? What is this number? This number we say is equal to what? Equal to 0, because I want to find the area between these two numbers. But these two numbers is 3 and 3s, right? So there's no area, so it's 0 here. Okay, let's take a look at number 7 here. It said, suppose f of x is a continuously increasing function, and let the L be the value of the Riemann sum using the left endpoint. Okay, oops. Let's try to erase it. Use the left endpoint here. Okay, use the left endpoint for each subinterval. Which one is true? Okay, so now let's take a look at these ones here. Okay, so what is this one telling you? So like in here, they said f of x is a continuous increasing functions, right? And then between this, between these intervals here, a to b, right? So it's a continuous in, and so I said, so remember, right? So I want to color code that for you. So the AB, right? So AB f of x dx is the true area for the curve, right? Under the curve here. Okay, so now let's take a look. Let's say the Riemann sums here, right? So if I divide this into several parts here, the Riemann sums here. So let's say if I use the Riemann sum of the left end, so this is my first interval for the left end, this is my second interval, this is the third one, this is the fourth one, right? If I use the left end, so the red one, this is my Riemann sum, correct? So this is my Riemann sum. Because this is the increasing function, so if you use the left end, your Riemann sum is always going to what? Always going to be less than the true areas, right? So what is here is ace here. Okay. Now, let's take a look at this ones here. What are the next ones here, right? All right, so for these ones here, they say, let's evaluate 3, 6, 12 minus x here. Okay, so we have not learned any integration skill yet, right? So let's take a look. So from the 3 to 6, 3, and here's a 6. When x equal to 3, what is the y? Y is 9 here, right? So y is 9. So this is 9. When x equal to 6, what is the y? Y is equal to what? 6 here. Okay. So this is my functions, right? So this functions here, this is 12 minus x function. Now I'm looking for the area between 3 and 6. So I'm going to find 3 and 6. So basically what I'm trying to do, I'm trying to find the exact areas here. And so because this is the lines, right? So I can really just use the what? I can use the area for the trapezoid, right? So I know these areas here will be the trapezoid. So what is the trapezoid? Is the half of the sum of the sum of the two bases times the height, right? So this will be the 1/2. So this basis here is how it's 9. This basis here is what? It's 6. Then what is the height? Height is 3, right? Okay, so now I can find the area. This is 22.5. So without knowing any integration skill yet, so I know this answer is 22.5 by just finding the area by using our geometry, what we learned before, and to find the area. Okay, so the next one is here. All right, so I guess I give you the, here, let's see here. I want to find the missing part, okay? So this missing part, this is x cubed, right? So based on our area principles here. So take a look here. All right, so I'm starting at 4, okay? I'm starting integrating at 4. And then I break several parts, right? Then I notice here, I'm ending where? I'm ending at the 7th here, right? So it's a 4 to 7, right? Because this is the ending point, right? And then for the second part, this integrals here, where I start 5, right? So I start 5, so this one's here. So this is my functions, right? So I'm going to find the area between 4 and 7. And then from here, the 5 to 7, this one's here, right? So this one is already given me this one's here. This is a 5 to 7, right? So this area is a 5 to 7. In order to find the whole area, I'm missing this part, right? So this part is from where to where? So this part is from 4 to what? 4 to 5 here, right? So that's why I can write this one is as the 4 to 5, right? So then what is here? This one is from the 4 to 7. So 4 to 7, you can break it into a one subinterval and another subintervals here. Okay, so I think now the last ones here, the true or false here, though this is a very good concept, right? All right, so let's take a look at the first ones here. The first one here is x times x squared plus 1. And they say, hey, I can take the x out. This is true or false? This is what? This is false. Why? Based on my principal area, I only can take the out is what? The constant, right? So take a look here, right? So because here they said dx, right? We talk about this dx is very important. That means I need to take the integration for all the x. You cannot take the x out when I want to integrate all the x's here. All right. Okay, so now let's take a look. The second one here. Second one, it says x to the t squared plus 1. So I have two variables. I have x and t. Take a look here. What I'm doing here, I am taking the integration for which variable? T. So if you take the integration for the t, then what is this x comparing to t? This x is what? This x is a constant. Because this is a constant, then I can take this outside here. So this is true or false? This is true because I'm integrating to t. And if you integrating to t, then the x is a constant. All right. So now let's take a look. This one is 0 to pi over 4, tangent x greater than 0. This is true or false? Well, I don't know any like the integration skill yet, but let's take a look at the concept. This is pi over 2, right? Okay, so I know my tangent graph is like this, correct? Okay, so this is my tangent graph. And then I'm integrating from 0 to pi over 4. That means I'm finding this area. And this is the above 0, so this area is a positive, correct? So this is true or false? This is true. Okay, So now let's take a look at the 2x. You integrate the same interval from 0 to 1, but here one function is 2 to the power x, and other function is 2 to the x. So then I say the 2 to the x is less than the x. Is that right? Well, let's take a look here. Let's do the same area principle again, right? So this is from 0 to 1. Okay, so when x equal to 0, 2x is 1 here, right? So 2x is 1. And when x equal to 1, this is 2, right? Okay, so this is so this function is my 2 to the x. Okay, so now I'm going to do a different function. So when the x here, when x equal to 0 is 1 here, 0 here, x equal to 1 is 1 here. So this is my function y equal to x. As you see, this exponential function is big, is higher, right? So now I'm going to find the integration. Now we use the integration concept. So what is the integration of 2x? I'm color coding that, right? So it's everything, everything is under the 2x here, right? And then what is this x here? The x is just everything under this ones here. I can try to color that, right? Now, which area is bigger? Of course, the pink areas, right? So the pink area is bigger. So that means this is what? This is false here. So this has to be greater than. Okay, so now the second one here, this is very important. So let's say x squared plus 1 dx, right, is equal to, you separate that, then you integrate that. So this is true or false? This is false here. This is the same idea when we use the product rule, right, for the derivative. So you remember that, right? So we said f of x times gx. If you want to take the derivative of fx times gx, the derivative is not just you take the derivative of x times derivative, right? So this is not, so if I want to find the derivative, this is not equal to f prime x times g prime x, right? That's why we have what we call this, the product rule. So for this problem, it's similar. That means when you take the integration of two functions here, right? So you have x and you have x squared plus 1. When you have the two functions, you cannot just say, hey, I'm integrating this function, then times integrating this function here, okay? That's it, right? So it's very, very similar like what we learned in the section 5.1. And we just said, okay, let the limit sum of the limit, and then we give a very specific term. We call this definite integrals. That's why we start to introduce this integration signs here, right? Okay, that's it. And now, for the next lecture, we can talk about one of the most important theory. We call this fundamental theory of the calculus. Okay, well, okay. Now let's take a break, and we'll come back for our next lecture note here. Right? Okay. Bye. Have a good day. All right. Bye bye.